Press the record so I don't forget today. I just took a 10-minute power nap at my desk. I feel refreshed, except I woke up with the hiccups. But so I went searching the lab. I found some sugar. They say like a spoonful of sugar cures the hiccups, and I didn't have a spoon, so I'm just like dumping in my hand, but gone, immediately gone. It's amazing. It actually works. So today we're being um, here at UNC. I'm being visited by my postdoc Rachel. Who's in the other room. I don't know if she's going to join us or not, but she came out and gave a talk to our education research group and is going to do some class observations and focus group. She's done a lot of these class observations and focus groups for, here she is, for the Opus curriculum. And she's coming out as she's here and going to do some for MWU before the termination of the grant and our writing of the next one. See, it's 3 o'clock, but we'll give it just a moment. How's everyone else doing? Accepted some of your students to Arira. Pull up my Arira list and see which ones. I have the notes here. Rachel and David. Joel Flores. Got accepted.
Yep. Joel Sotelo Flores.
Yep. And Andrew Alexandra Selesky got accepted. I think that's it right now. I just sent out the first wave. We'll see who accepts and who doesn't. Super competitive this year. We had 80 applications for 20 slots. So 4-1. All right. Okay, so I was saying, as many of you were coming in, I just took a 10-minute power nap at my desk. And so I'm waking up here. But let's see, where did we leave off? Let me share. Unless anyone has any issues they'd like to discuss, I will share. Slide this over here. So the goal today is to finish Module 3. We've been working on this for a while, so it'd be nice to crank through it so we can move on to other things. We'll probably go into mid-May, for whoever wants to. We're a little bit behind my class and still lots of stuff to share on the MW front. Afterglow. Okay, so over the previous couple sessions, I think we had a week off and then we had an AI week, but slowly but surely we built up this image. This is just the one we demoed with, but like all my students, I have 25 teams and each team picked a different target. And we'll see some of their results, not their image results, but their calculation results in a little bit. But this is the one we all did as a walkthrough. Maybe next year I'll pick a different target, keep it fresh for anyone who comes back. But I love this one. This one's fun. And we learned how to do the RGB combo, the LRGB using the luminance layer, how to fold in the narrowband layers, which gives us temperature information of the ionized heated gas. We learned how to grab infrared data, both near infrared, like dust-hidden stars, and mid-infrared, which is star-heated gas that's glowing, like the orange here is Spitzer, as is the blue. And put together this awesome image. And then we started working on interpretation. Start with calculational interpretation. Let's see if I have my doc cam up. I do good. Yeah, that fits. So I won't redo this derivation today, but we'll use the equation. So there are two calculations you can do off of an image like this. One is a Stromgren sphere calculation. Uh, and just, the basics here, you got stars, they're producing ionizing radiation. Ionizing meaning greater than 13.6 eV, so it can knock electrons out of hydrogen. And it just keeps cranking out these photons, and so you have this ionization region that populates. But the protons and electrons, once ionized, they try to recombine at a certain rate, and you hit balance at a certain distance. So you get what we call the H2 region. That's the ionized hydrogen region. Outside, you have normal H1, not ionized hydrogen gas. And so by setting the ionization rate to the recombination rate, we derived this equation. And I'll skip the derivation. We did the derivation last time. And so here's the equation we ended up with. We're going to start by using it. So what are we calculating? Calculating the density inside this region. And it's a function of two things. Once you work through all this math, the size of the region, we'll start with that. I'll show you how to measure that off your image or out of stellarium. And the rate at which your hot stars are producing ionizing photons. That's a little trickier, depends on spectral types and how many there are. And we'll use a little AI for a boost there. Try to. It's actually going to be a good test. We'll all put in a statement into our favorite chat vehicles like ChatGPT and see how consistent the results are. Anyway, once we know the size of the region and the rate at which it's producing ionizing photons, because the ionization balance, ionization recombination balance, we can calculate that internal density. That's the first calculation. We'll do that, and then we'll derive the second calculation, which is pressure balance. So this region, being hot gas, will expand until it's in pressure balance with the external medium. And that happens pretty quickly, in about 1% of the star's lifetime. So most of these regions are in both recombination balance and pressure balance. And kind of the nice thing is between these two equations, we use every piece of our image, the stellar layer, the narrowband star-heated gas, the mid-infrared dust-heated gas. And we get numbers that we can check against reality in two different ways. Okay, so first thing will be the size of our region in parsecs. And feel free to interrupt with questions at any point. Okay, so if you have your image up in afterglow, there are basically two cases. Does the whole star-forming region fit in my image? If so, you can measure it in afterglow. If not, we can use stellarium. Let me demo afterglow first. So if you have your image up, but I sent around the images last time. We did this together, and I saved it and sent it to you in case you don't have it up anymore. You can download it and upload it. Or if you have any prior version, you can just kind of make do. So 3 tabs down, so 4 tabs down, we have the plotter tool. It does a number of things, but you can measure distances. What we want is kind of the typical distance of our H2 region. The distance from the ionizing stars out to the wall here. And so here are my ionizing stars. I click, and then I have a little measuring tool. We use it in Opus to measure distances between planets and moons and things like that. And you want to kind of measure the distance out to the outer wall. Maybe I'll change my orientation. Kind of match reality. And, in this particular image, you have columns and no, these are columns. No, these are columns. column, spire, pillars. Over here we have pillars. Here's a spire. Here's a column. Bumps and lumps. You don't really want to go to them. You want to go to the outer wall, which is just barely on the edge of the image. Kind of take an average, maybe something like this here. And you come down and you can read it off in arc minutes. This was about 8 arc minutes. This is very crude. Everything in this calculation is going to be very rough, but it's okay. That's how astronomers roll quite often. So 8 arc minutes, and we want it in degrees. And we're going to stick it in this spreadsheet. So let me share this again. Put it in the chat. We're all doing the same object. Now, my students use the spreadsheet to do different objects. And we'll keep checking our stuff against them. But we're all doing the same object. So anyone who is bold enough to do calculations with me today, go ahead to the spreadsheet and add your name. And your target's the eagle. We're all doing the eagle today. But hopefully a few of you will be bold enough to follow along and contribute. Yeah, wonderful. Yeah, Matt has to because these are his equations and calculation that I'm sharing, so he has no excuse. I mentioned this before. Matt developed this part. Okay. And so the Stromgren radius, and so you put that here, and that's in degrees. There are little notes over here. It's the radius you measure in arc. If you're using Afterglow, it's the radius you measure in arc minutes divided by 60. So that's one way you can do it. And so I measured about 8. It was like 7 point something, but I'm just going to round off. So I got about 0.13. Now, while you're doing that, and feel free to measure your own. You don't have to take mine. I'm going to show you how to do in Stellarium. So you bring up Stellarium, turn off the ground and the sky. And you might want to put in equatorial. That will frame it up the same orientation as yours. So I'm going to go equatorial. And then I'm going to search over here. It's the 4th one down. Searching for M16 in the plane of the galaxy. And there it is. They have these little thumbnail images almost. And you can zoom in. There's the same, my picture was right here. And let's assume that our field of view is so small I didn't really get a good measure of the cavity. You can get a crude measure. You put the top of the cavity on the top of the image, the bottom of the cavity on the bottom, and there's some ballparking. And you have a field of view here, and that is top to bottom distance. So, again, it's very eyeballish. And the eagle kind of is at the cusp. It works for both techniques. And I got 0.2 degrees, and that's the diameter. So for the radius, you'd cut that in half, and it'd be like 0.1 degrees. That's another way you can do it. Point 0.2, and like this one was 0.13, the other was 0.1. Anything in there is fine. The beauty of this calculation is the numbers don't have to be very exact to get very reasonable results. Okay, so that's the Stromgren radius in degrees. And for the equation, we need to get it in parsecs, a physical radius. And so we start by looking up the distance to the thing in parsecs. And we can just go to Wiki for that. Eagle Nebula Wiki. And usually they have a distance right here. So here it is in parsecs, 1740. And it may seem like a cheat just getting it off Wikipedia, but where'd Wikipedia get it? They got it from Gaia. And it's worth pointing that out to your students because they're familiar with that from Module 2 when they did star clusters. They understand how the distances come to us. 1740. Yep, you're all way ahead of me. Okay. And so then the Stromgren radius in parsecs, we use the small angle formula. I have it over here. You take the angular radius in degrees, divide by 180 degrees, multiply by pi to get into radians, and multiply by the distance away in parsecs. And that gives you the radius in parsecs. So you all can code that in, or wait for someone to code it and then just drag and steal it. But let's see. What I say it was the angular radius divided by 180 times pi. With pi, you can type in pi, but you got to do the parentheses there. Puts in radians times the distance. Yeah. So getting about 4 parsecs. Clues, check your math. Clay, check your math. Something.
I do it piece by piece. I
Oh,
just did the first part.
okay. Okay, cool. I see. I guess you and Clues are doing the same thing. Nice. All right, great. That's it. Okay, so we've established the size of this region. It's about 4 parsecs across. Remember, parsec is a typical distance between stars in our part of the galaxy. Like us to Alpha Centauri is 1.3 parsecs. That gives you kind of a relative scale here. All right, that was the easy part. Again, to remind you of the calculation, we need a physical size. Now we need the rate at which the stars in our star-forming region are producing ionizing photons. Okay. Now this depends very strongly on what kind of star they are. Let me see if I have a, where's that? I think it's behind you all. Yeah, let me find just a basic thermal spectrum. I know I have one in this folder. There we go. Basic thermal spectrum here. So O stars are very hot, like 50,000 or something. So they peak way over here in the ultraviolet. 13.6 eV is somewhere up here. So if you have an O star, you have lots of ionizing photons. But as the star gets cooler, because of the exponential cutoff, you very quickly lose those ionizing photons. So it's very sensitive to spectral type. And if we go to page 2 of our little Stromgren sphere calculator, I have little calculators ready for each of you. But here's kind of a table. O stars are the most massive, hottest stars. And you're working your way through the spectral subtypes, O4, O5, O6, O7, O8, O9, getting less massive and cooler. Then you hit the B stars. So this table covers O4 through B2. Here are the masses of the stars. And here are the corresponding temperatures and the ionizing flux that you get out. This is for a star of this temperature. And mass, that's how many photons per second that you get that can ionize. And you see, as you drop down in mass, it drops pretty quickly. This is 10 to the 44. It's 5 orders of magnitude below 10 to the 49, 100,000 times less. And so what we really need is to know how many O4 stars I have, how many O5, O6, etc. And it's really just the most massive ones that matter. You could be way off with the numbers down here. It's so few ionizing photons. Whether I type in 10 or 100, it doesn't matter. It's really about the number of the high mass ones. So how do we do this in a class setting? So looking at the image here, I can't tell. Is that an O4 or an O3? I don't know. And some have a lot of O stars, and some star-forming regions the students do, like Demarin's object off the Orion Nebula. It's just one tiny little B star. It's a really small Stromgren sphere. Anyway, so what I've ended up doing is going, what the students ideally do is they search and review the literature and read papers, but we don't have time for that. So I say we're going to take a quick stab here, and if they want, they can do literature searches and whatnot. So we use AI, and as Clay taught us, it's about asking a good question. I'm gonna slide you all back over here so I can see Clay as I do this. If she smiles or frowns, I'll know if I'm doing this right. And so here's the question as I phrased it. How many stars of each spectral subclass from O4 through B2 are in the Eagle Nebula? If you're doing a different nebula, the students swap out the name. Give me your best guess in the form of a table, subclass versus number. This seems to work for me. If you don't tell it to do the best guess, it will kind of say, well, this is kind of hard to do, and you may want to check the literature, and it will punt. But if you tell it, give me your best guess, and you may have to ask it twice, it may hedge a little bit and say, just give me your best guess. It will give you a best guess, and we're going to find out how consistent it is. This is a good test. We'll all do this if you have access to chat or something similar. So I'm going to put that question in the chat and pull up your copies of ChatGPT or whatever you prefer to use. And again, what I find is it's fairly good with the top of the table where it matters, and it's more approximate at the bottom where it doesn't. And hopefully, without too much prodding, you may have to prod a little bit more. Let's see what we got here. Great. So Matt's given a paper. Is this for the Eagle Nebula? Yep. But remember,
It's the one we used originally, and the one I use for the class. So
though, of course, each student's doing a different region. And
sure.
So, yep.
Yeah.
Maybe we can find the ideal paper for each region and include that in the table. That would be nice.
Independent study project. Thank you.
Yeah. Yeah.
I'm liking it.
But short of that, this will be a good test. Go get your numbers and stick them in the in one of the calculator tables, and we'll see how consistent we are. So okay, yeah, you can claim it with your name so we don't start overriding each other. And this is a hard thing to test by yourself because chat remembers prior conversations and it can get biased based on what it already told you. It may be defend its numbers. And so we'll see how much our total ionizing fluxes differ. Like Kent is finding many more stars. And also, it may not just be chat hallucinations. It may just be, how do you define the Eagle Nebula? Where's the extent? How far out do I stop counting these stars? So far, we got a 2e to the 50, a 1e to the 50, a 1e to the 50, 1e to the 50, and our ones are almost 2e to the 50s. 4 people so far have plugged in numbers. And, oh no, there's more down here. Here's another. These are remarkably similar. Kent's is a little higher than everybody else's, but everything in this calculation is really almost order of magnitude. And we're getting stuff that's within tens of percents of each other. So that's encouraging. Okay, so once you have that ionizing flux, you can go back to sheet 1 and stick in your ionizing flux. Let's see, mine was 1.43 e to the 50. And after we calculate this, we'll compare it to other star-forming regions that my students got. So far, I'm pleasantly surprised by the numbers I see here. AI seems to be an effective tool. Remember, yeah, the earlier versions were more prone to hallucination, and the more complex the question is, it can still hallucinate a little bit, but it is trained off the sum of human knowledge. And so it's like a very rough review of the literature on something like this, if you ask the question well. Oh, please.
I'll point out that Copilot's being quite obstinate about not wanting to provide the numbers.
Okay, interesting.
So it must be trained off the sum of politicians' knowledge or something,
Yeah.
'cause it's avoiding the question.
Trying to be careful. Chat would avoid it as well until I just keep saying, just give me your best guess. Calais, you were going to say.
Well, what I wanted to do for this last year and made a little bit, but not enough progress to implement it, was to have them look up at the stars in Gaia. And I figured that would be just the definitive answer, because you could define the region of interest, set a radius and just tell me all the stars. You'd have to figure out which ones were at the same distance, but you can filter for that. And then just look at the bright ones. And I got really confused because I think there was just all the reddening messes it up, but figuring out which stars were which spectral class based on Gaia data was not yielding any blue stars.
Oh, wow.
Actually, I threw up my hands, and I'm sure it's a reddening correction thing, but I couldn't figure out kind of how to get around that. Maybe from a cluster fit of the region, or just guessing reddening values, or maybe AI knows the reddening values too. I hadn't thought to ask it for that.
Interesting. In here, I'll just pop the student results for a second. Running Man Nebula, it's just a single B star, and see it's very low. Let's see, Demarin's object should be in here somewhere. Here it is, Demarin's 10 to the 47. But a lot of people are getting numbers similar to what we have. Tarantula Nebula, which is huge, and it's 10 to 51. That number is clearly wrong, but anyway. Yeah, just looking at this here, their sizes in parsecs range from, that's distance, size in parsecs. Few parsecs, Tarantula's huge, and some things are tiny, like Demarin's will also be tiny. Because again, just a single B star floating it. But yeah, they're getting a nice reasonable range of sizes, ionizing fluxes. And so interior densities, let's calculate that. And we're going to use this equation here, which I have written off on the side. And so we can start plugging this stuff in. Now I'll let you all do your calculation. Let's see, I'm first one here. So equals 540 per cubic centimeter. Again, astronomers, they're CGSers, which may confuse some of your students. And then I got the ionizing flux, 5 by 1 E49, quantity raised to the 0.5. If you raise it to a fraction, again, I think you have the same problem. Make sure if you raise it to like 1/2, make sure that 1/2 is in parentheses. Students will often miss that, whether it's Excel or calculator. So often I tell them to use 1/2 and minus 1.5 instead of fractional exponents. And then the size in parsecs right here to the minus 1.5. Okay. Yeah, I got interior density of about 100, 200. We'll see if you get similar things. Then check your math.
While people are entering this in, Dan, can
Yeah.
I just ask a sort of big picture question? So everything that you're doing here, is this based at all on the photo we were looking at, or are the numbers that are being calculated just coming from the estimates from Chad about how many different spectral classes we had?
The size came from the photo, The
Right.
spectral classes, yeah, we borrowed that from Chad because our photo, we can kind of count the number of bright stars, but you can't see the spectral class. But most of the rest of the calculation for the outside density, the columns to come, will come from the photo as well.
Okay.
Most of the rest is temperature dependent, and the different layers give us temperatures. Okay, great. So we're all getting densities there. And just to give you clouds out there in space before ionization are typically 10 to the 2 to 10 to the 4. So like 100 to 10,000 particles per cubic centimeter. And inside the H2 regions, it'll be lower because the hot gas expands. So maybe 10 to the 1 to 10 to the 3. And so our case here is right there, smack in the middle. And we can look at student results for interior density. And sometimes they're getting low ones. But again, most of them are between 10 to the 1 and 10 to the 3. So it's very good. And we'll do an independent check here in just a moment. While you're finishing up, let me derive the second part of the calculation. So the first part is the interior density, and the second part is the exterior density. So exterior density, I will go to the dot cam and derive it for you. Okay, so I think I have a light. Yeah. Okay. Oh, this map sucks. Better. So here are the stars again. Here's the H2 region. In here we have a density NH plus ionized hydrogen. This is our H2 region. Now out here we have a density. It's actually colder out here. It's not atomic, it's molecular. It's cold enough that the the hydrogen atoms bond up into diatomic molecular hydrogen. And this is hot, this is cold, and so hot gas expands. And will expand until you've established pressure equilibrium with the outside molecular gas. So we're going to calculate the exterior density under two extremes. One extreme is it just turned on, and so it has not yet reached pressure equilibrium. That one's easy to do, and then the pressure equilibrium is more likely the correct value. It only takes about 1% of a star's lifetime for the H2 region to establish pressure equilibrium. So 99% of the star-forming regions that we look at will be in pressure equilibrium. But initially, basically, the density on the outside is just half the density on the inside. Why is that? Well, these are number densities, not mass densities, number densities. And, out here we have molecular hydrogen. And in here, it gets ionized. And so previously you had two protons together in a particle, and once it's ionized, they're separated. So and so the outside density will be twice. Everything's ionized, and so I'm just pausing for a second. Why is it not format? Oh, it's not the number density of all particles. It's the number density of the hydrogen. Yeah. Okay. So sorry, I was thinking about where are the electrons? Yeah, it doesn't matter here. So for every molecular hydrogen, every molecule of hydrogen out there on the inside region, because the ionization, you now have two protons, where before you had one joint. So initially, the density in here doubles. Well, that means since we've already calculated the inside density, initially the outside density is twice the inside density. I feel like I did a terrible job of explaining that, but everyone know what I'm saying here? Okay. So that one's easy. We can stick that in the table. But again, it's not the realistic one. The outside density is just the inside density divided by 2. And so most of you got that here. So it starts out with kind of a slightly lower density. Well, we're inferring, initially based upon what we measured here, we can infer a lower density, but that's a lower limit. The upper limit will be after pressure equilibrium. Oops. So let's derive pressure equilibrium. And this is where I just love how all the pieces of this, all the astrophotography, all the layers, it all folds together. And so we're going to use everything else in this part here. Pressure equilibrium. The pressure of the H2 region equals the pressure of the H2 region. So it's notationally a nightmare, right? H Roman numeral 2 is the ionized hydrogen on the inside. H lowercase or H sub Arabic 2 is the molecular hydrogen density on the outside. In pressure equilibrium, you expand until these pressures are equal. Now, the pressure on the inside, it's the pressure of the protons and the pressure of the electrons. You have 2 sources of pressure there. So everything's ionized, and for every proton in there, you have an electron in there. Okay. Now we'll use ideal gas law, which they all know all the way back from high school chemistry. So the pressure of the protons is the density of the protons times K times the temperature on the inside, that H2 region. Pressure of the electrons is the density of the electrons times K times the temperature of the inside. And that's going to be equal to the density of the molecular hydrogen on the outside times K times the temperature on the outside. Nothing fancy yet. Cancel out the K's. And we'll use the same trick that we used before. The density of the protons on the inside is the same as the density of the electrons on the inside, because it's all started neutral. It got ionized, so you have the same number. For every proton, you have an electron. And so you can rewrite this. I'll do it in 2 steps. I try to make, I try not to combine steps with the students. I just factor out the 2 ends. Then I point out this density, this number density is the same as that number density. It's not mass densities, it's number densities. So we can then say 2, the proton density on the inside times the temperature on the inside is the molecular hydrogen density on the outside times the temperature on the outside. Or solving for this, that's what we're trying to get to, the density, because we already know the density on the inside. We just calculated that. Density on the outside is equal to the density on the inside times the ratio 2 temperature on the inside divided by temperature on the outside.
Dan, could you explain the H2 and H2 again? I just am getting, I think, confused by the notation.
Yeah. H Roman numeral 2 is the temperature in the H2 region on the inside. H sub 2, that means molecular hydrogen gas. So the Roman numerals, I'll just make a little note here. Neutral gas is called H Roman numeral 1, ionized hydrogens H Roman numeral 2.
Okay.
And so those are kind of one notational thing. And then another notational thing, N sub H2 is, well, sorry, we don't need the N. H2 is molecular hydrogen.
I see. Okay.
You can have just H by itself, that's atomic hydrogen.
Yeah.
The H1 is referring to any of this stuff on the outside.
Could we, would it be correct to say, instead of putting H Roman numeral 2, to say P H plus electron
Yep, you could do that if you want.
as the first step?
P plus electron.
Okay, just making sure I get that.
This
Yeah.
P, yep. There are
Okay.
different ways you could do the notations here. All right, so we have our equation. Now we just got to figure out where these temperatures come from. Temperature inside, temperature outside. So on the inside, running out of space, but I'll write small here. The inside temperature, well, we have our narrow band. We have H alpha, we have S2, we have O3 gas layers, and they all glow under different temperature ranges. For H alpha, it's like 5,000 to 10,000 Kelvin. For S2, it's about the same, a little bit higher, 8,000 to 15,000 Kelvin. And for O3, it's 15,000 to about 40,000 Kelvin. For example, if you're hotter than 40,000 Kelvin, that O3 gets ionized into O4. So you don't see the O3 line anymore. And, you know, if it's colder than 15,000, you have O2 instead of O3. Here, I'll pull up another picture just because it's kind of really illustrates this. Oh, where is it? Yeah, here. This is the Rosette Nebula. And in this color scheme, the oxygen is blue, the hydrogen is green, and the silicon is red. And so you can see in the middle here, there's nothing. It's because it's hotter than 40,000 Kelvin there. And the region from there out to here is 40 to 15,000. And then you see the hydrogen and the silicon. You would expect to see the silicon first and the hydrogen further out, but often you see them flipped because silicon is also very sensitive to density. And so as you're moving out of the bubble up into the surrounding denser clouds, that actually has a stronger effect and makes the silicon shine out there. Even though it's sensitive to hotter temperatures, it's more sensitive to higher densities. So, you know, you can read temperature information just off of your image and also some density information at the edge. If you get the hydrogen and the silicon flipped, you know, you would expect it to be oxygen. It's not silicon. I've been doing some other research about end-stage nuclear burning. So I've been focused on silicon. Oxygen is the hottest, sulfur is the next hottest, and then hydrogen, you expect them to be in that order. The fact that you sometimes see these flipped in the outskirts means you're going up a density gradient. It's a great temperature and density information. Anyway, what you do is you look at your image. Let's bring up our image and see which, you know, right at the edge, the boundary where it's up against the higher density gas, but on the inside, what do we see most of? In our case, it was mostly H alpha out here. This kind of greenish color, that was what we chose for the oxygen. It's more on the inside, but here on the outer wall, the pink is primarily H alpha. And so in the table, the students look in their image, and most of them it's H alpha in the outskirts, but sometimes it's something else. We have at least one O3 in here as well. But for us, it's mostly H alpha, so we indicate the narrowband emitter on the inside boundary. It's H alpha. And that means the temperature on that inside boundary is somewhere between 5 and 10,000. You can take something in the middle or maybe on the low side because we're all the way out at the edge. So in the middle would be 7,500. Maybe I'll take like 6,500, something like that. Anything in that range. If you see some oxygen mixed out there, maybe you go a little bit higher. Yeah, it's whatever you think. Something in there will be fine. And that's our inside temperature. We're using our narrow band layers to measure temperature. And then on the outside, we're going to use our dust layers. And in this case, here, I'll put some more notes on the dog cam. And I got a video that goes through all this same stuff, same notes. So don't feel like you have to remember it all. It's all there. We tried, so this is the outside temperature, N sub H2, molecular hydrogen. We tried Spitzer 8. We tried Weiss 12. These are microns. We tried Weiss 22 micron and Spitzer 24 micron. And so we need to look at our image and see which one really dominates right on the outside wall. Now, for this particular image, we use the Spitzer data, 8 and 24. And here the outer wall, the Spitzer 8, we colored orange. And that seems to be what's dominating. There is some colder Spitzer 24 floating around in various places, but on the outside of the wall, it's a lot of Spitzer 8. So we go here and we mark out here, it's Spitzer 8. And to figure out the temperature, we're just going to assume it's kind of near the peak of the black body. If the Spitzer 24 was near the peak of the black body, it would have showed. It didn't really show, these showed. So we're going to assume it's near the peak of the black body. Put up the dot cam. Totally mismanaging my, what's this? There we go. Mismanaging my paper real estate here, but here, I'll just draw. Yeah, I'll put these notes right here. So the black body curve, remember, it had that rapid roll over. Pull up the image again. There we go. Black body curve, log intensity versus log frequency. We have the Rayleigh-Jeans limit rolls over into an exponential cutoff. And where this thing peaks is given by Wien's law. So I'll just write that down. So here we have log frequency. Here we have log intensity. This peak right here is given by Wien's law. The wavelength in, oh hell, I just go to my other notes because I used the paper better. It's the same stuff. I just used the paper better. So there we go. So there's my little black body curve. Wavelength in microns is 2900 Kelvin divided by 2. That's Wien's law. Or if we solve for the temperature, this is the outside temperature. It's equal to 2900 kelvins divided by the wavelength in microns. So we found a lot of Spitzer 8 out there. So I'm going to take 2900 divided by 8. And that's going to give me my outside temperature. That makes sense how we got that? It's rough. We don't know if this is exactly at the peak, but probably close. While you type in that, I'll show my students' results. They had a bunch of different things. Sometimes Weiss, sometimes Spitzer, sometimes the lower micron, sometimes the higher. So here they're calculating, but you always get something between about 1 and 300 Kelvin, depending on those options. And so then you can go and calculate that exterior density. Again, here's the equation right here. It's just your interior density, which we already calculated, times 2 times the interior temperature divided by the exterior temperature. And I'm sure I have that over here in the notes. Yeah, all that information that I wrote, it's all right here. But here you go. The exterior density is the interior density times 2 interior temperature, exterior temperature. So interior density times 2 times interior temperature divided by exterior temperature. So in this case, I have about 10,000, 9,000. Again, star forming regions are between 100 and 10,000, a little bit below 100 to a little bit more than 10,000, 20,000, 30,000 at most. So we're all getting numbers kind of in that range. We disagree by a few thousand, but still, we're getting 10 to the 4. While you're calculating those, I'll show you what my students got. Exterior densities, everything between about, there's a couple that are low, but most of them are around 100 to around a few 10,000. Here's some 30,000, here's a 60,000. But most of them are 10,000 or less. Well, yeah, tens of thousands. And then going down to, a few hundred. So they got stuff in the right range. So that's one of our checks. We figured out the density of the exterior cloud under the limit of pressure balance, and they're getting densities that are quite reasonable for clouds in space. That's one check. Now see how we did here. We have some uniformity. We do. And so pause there, and then I'll mention the second and final check. It's pretty easy to do. Questions about any of this? Okay. The second check is on the inside. We have a lower density than the outside, but still pretty high density. And the typical density of interstellar space in the galaxy is about 0.1 per cubic centimeter. And we're getting stuff, well, we all got like 200 because we're all doing the same region. And so it's pretty dense in there still, and it's ionized. And that means you're going to get Bremsstrahlung radiation. We talked about the different emission mechanisms, the different continuum mechanisms. A black body, the one we're most familiar with, but also synchrotron, due to charges going around magnetic fields, and Bremsstrahlung. And I'm looking for the little Bremsstrahlung figure here. Pull up, remind you of Bremsstrahlung emission. Here it is. Loaded as paint. Not sure why. If you have free charges, that's sometimes called free emission. You have free charges. When they pass each other, an electron passing in a proton, it deflects, it decelerates, and the energy difference is released. And if it's a dense region, then you get a lot of it. And so star-forming regions like the Eagle, or like any of the ones my students looked at, should be spitting out Bremsstrahlung radiation, which emits in the radio. Okay. So I then have my students go back and do a little radio map, just a 6-beam by 6-beam map. And we've done a couple radio maps already. We've done big ones. We've done small ones. And so here's one right here of the Eagle Nebula that I did. In fact, I'll give you all the URL so you can go through this final step yourself. Find the chat. So this is the completed observation. You can look at the preliminary data products. Doing just a little map. It's kind of messy. Really kind of ugly, actually. But there should be something near the center. Appears that there is. Let's try to clean it up. That's 21 centimeter emission. That's a little bit of RFI. But anyway, I've already processed it. I have it set here. I used both channels. I skipped some, those two frequencies, did a faint target map, and you can just download it. It's, click on this last one here, download it, and upload it into Afterglow, and it'll be all kind of cleaned up and corrected. Messier 16 job, let's see, 6043. Just want to make sure that's the same one. Yes, 6046, I think is what I meant to say. 6046, yep. So you can download that and put it in your workspace and open it. And here it is all cleaned up. Here's the raw down at the bottom. That looks a lot like the preliminary data products that we saw from Greenbank's page. Time shift messed up and all sorts of stuff. But after we do all the cleaning and correction, looks pretty nice. There's something brighter to the bottom. But right there in the middle of the field, radio emission. Because we calculated a high density, a high temperature. So it's ionized. And so there should be radio emission and confirmation. There it is. Now just keep in mind that our optical image, I'll put these things on the same scale here. So here's the radio image. There's the optical image to scale, right? Our radio maps are very blurry. There's an offset, and these radio maps are often off by a degree, a fraction of a degree. But that field is really small, about the size of my cursor, coming from right here. And yeah, it's a radio emitter too. It's a multi-wavelength universe, tying it all together. Questions about that? Then I'll just mention, we won't go through it, but the last bit is image interpolation. So that's kind of the quantitative stuff. The things we can measure. We can measure densities, temperatures, and do fundamental physical calculations. But then I have the students also do some interpretational work. And I'll just point you to the videos. There are kind of two types of regions they typically do. One are regions like the one that we just studied, which have pillars and columns and spires and globules. And in this video, I kind of tell the story about, well, how these stars here, they ionize the gas and the gas starts expanding, but it runs into overdensities and kind of expands around it, creating the pillars, and then it starts squeezing in from the sides, eventually turning it all into stars, collapsing all of the clouds, creating the next generation of stars. And you end up with those dense fragments all by themselves. We call them globules. You see examples here, for example. This had a column behind it at some point. And then that's the next generation of stars that continue the process. So more detail in that video. And then the other type of object that your students will often do, maybe I'll bring up an image here. Some of them do reflection nebulae or have other forms of dust in their image. Here, I'll just pull up. Here's kind of my slide deck on columns and spires and how they sometimes create stars, Herbig-Haro objects. I'll skip all this in the interest of time. But in some of the star forming regions, you see little jets from new star formation. But then the second class of objects has to deal with dust, both line of sight dust. Like here we have an H2 region. It's glowing pink because of the H alpha. And blue I'll come back to in a second. And then you have dust that's line of sight. So it's being backlit and made dark by the light behind it. And here it is in the infrared. If that dust is close, it not only blocks it in the visible, it's heated by the stars in the infrared and will glow in the infrared. But then you have things like this blue region that's a reflection nebula. That's not line of sight dust, that's off the line of sight foreground dust. So some of this radiation comes out, goes in this cloud, and it, just like our atmosphere scatters blue everywhere, it scatters the blue light everywhere. The red continues on over our disembodied head here, and you don't see it, but the blue gets scattered everywhere. So often with these star-forming regions, you'll see blue reflection nebulae, which are due to foreground clouds off the main axis. And that's what we see here. And you can tell that the cloud is very foreground because it's not close enough to be heated by the stars, else it would be glowing. Sometimes it glows. Sometimes the reflection nebulae glow in the infrared. I think I have an example. Yeah, like here. Here's the Horsehead Nebula. And the stars are off the top of the image that's heating all this H alpha here. But here you have a little reflection nebula, just kind of one star there. And the blue light's getting scattered towards us. But the dust that's doing that scattering is really close. And so it's glowing in the infrared. What's interesting is the Horsehead is not. That Horsehead is actually well in the foreground. Or else it would have been heated up, same as this other dust. Anyway, your students can start to, whatever their image is, whether it's more like the Eagle Nebula or more like what we're seeing here, they can tell a physical story about what's going on. It's a quantitative piece and qualitative piece. I'll stop. So we're at 4, but comments, thoughts?
Well, we're just kind of going back and forth in the chat about the number density and how it's maybe not the most physical quantity. And I was just getting ready to type, and so I just thought I'd say it since you paused, that I think the important piece and the science piece in particular is getting this upper and lower limit and understanding that oftentimes there's not a right answer to these things, that we're oftentimes constraining quantities, which I think is a real science idea, and particularly in astro, where we're employing the cosmological principle and such to make any sort of calculations. But anyway, that's what I was just going to say, to Calais and Clues in particular, but everybody's obviously included.
So
also-
one,
No, go,
I'm sorry, Dan.
I was just going to say, the pros, when they come up with their density measurements, they're doing the same thing, and they're just as inaccurate as these.
And so a comment I wanted to make from something Dan said earlier, he uttered a phrase, and I'm not going to hold him to it. I'm not going to say that it was necessarily intentional, but he said we can calculate temperatures and densities and sizes. I think maybe estimate is a better way to phrase that, because many of the numbers that we worked with, it's not that the numbers we've used were unphysical. It's just that the error bars that are on these numbers are pretty big. But by having some of this knowledge and some of this background, we can estimate using numbers that are reasonable, and we can come up with an answer that's reasonable. And so I think we want to be careful that we don't overstate that we're like, I know it's a subtle distinction, but
That we're actually measuring things, right? I mean, this
Yeah.
is to your point, Clues, I think.
It's a back of the envelope calculation, an order of magnitude estimate, however you want to put it. But we didn't come up with densities that are like neutron star densities
yeah.
or galactic halo densities, right?
And there's a thing that we do as astronomers kind of all the time, that we do this kind of thing where we're like, okay, we'll grab some reasonable numbers, we'll put them into this equation that we know that that's what's going on, and we come up with a number that's reasonable. This kind of back of the envelope thing that a lot of, at least undergraduate students, they're super uncomfortable with it. Like, they want the answer from the number. And it's like, well, that's not really how the real world works. Like, sometimes we're working with partial information and we just got to make do, but that doesn't mean we can't do science with it. It just means that we've got to be careful with it.
If we could take the nebula and bring it into our lab, we can make some pretty careful measurements. Thing is, it's so far away, we just have to work with what we have. And so this is what astronomers do.
Yeah.
If they're uncomfortable, good.
And we can't even acquire the number densities, even if we could bring that thing here. It's the number densities, because the nebula is so large we can't even achieve those number densities on Earth. But
it's not spherical, it's not smooth. We have a stuffed cow over in the other room that is a sphere. It's our spherical cow. How does a theorist approximate a cow? As a sphere? So anyway,
yeah, there's also some good discussion about significant figures and how imprecise these calculations are, and how we need to remind our students that just because the calculator spits out 17 decimal places doesn't mean that we need to obey the calculator. But yeah.
Yeah.
Yeah, I was just working with a student this morning who's trying to understand some eclipsing binaries, and their Roche lobes are like, you know, within a very short distance of each other. And he's like, okay, so they're not contact binaries. And I was like, you know, they're like really close. Maybe they're like barely outside that threshold, but I think that's a little premature to say. One thing I was wondering, I like this. I don't do most of these calculations, so the spreadsheet is useful and I could see myself maybe attempting it now. But I do the temperature. I do the radius and the temperature only, and I do it from images that they find online. But one thing I was wondering about is the designation of the region as H alpha O3 or S2 based on the brightness, because we don't calibrate narrowband, right? Or is there a way to do that I
Yeah,
missed?
so we colored each of our narrowband layers a different color. And
Mhm.
the images out there, they often use the Hubble palette, like the rosette image I showed you. The blue is oxygen, green is hydrogen, and red is sulfur. Just from the color, and for this calculation, it's the color at the boundary. Whichever color is dominating at the boundary is giving us the temperature at the boundary.
But do we know that the brightest color means that there's more of that element? Because what if it just, there's more of it, but it doesn't emit as much? Or, I mean, I get that it's hand wavy, so that's fine if that's what we're
Yeah.
doing. But I just wondered if there's any way to quantify amount based on color
So the
for.
amounts of the H alpha, the O3, the S2, I'm sure there are probably ways to get estimates of them if you involve some atomic physics. We haven't sorted through that.
Yeah, that's
Just
fine. Just
looking
wondering.
for but usually they have certain spatial extents where they dominate. And like the oxygen is usually disjoint from the other two because they're probing different temperature ranges. And so I'm just seeing which is kind of dominating at the contact point. And if they can't decide between H alpha and S2, doesn't matter because they both shine over the same temperature range, essentially. It's almost a bimodal choice. All right, so we won't be meeting next week because my postdoctoral mentor, Shri Kulkarni, is coming to visit.
Dan, can I ask an off-topic question about
Yeah.
Afterglow that you will feel very confident in being able to answer?
Okay, good. Yeah, sure.
I have my students taking some photos from our observatory as we've been like communicating back and forth on, and I was trying to get them to use the WCS calibration tab in Afterglow to plate solve.
Yes.
And I don't know if I'm screwing something up or whether there's a bug here. Can I share my screen and show you what's
Yes.
happening?
Go for it.
Okay. So here we go. All right, can you see that?
Yes.
This is a picture of M13 mono photograph. And so I can choose my image.
Mhm.
It comes in with like default values down here, but I can't edit these.
Uh,
Um,
Press the extract values from current viewer.
so when I do that, this is what happens. And then if I try to type in here, nothing, I can't type
Okay.
in there. I can so my image comes in without any
Yeah.
info, and I don't know how to add it in. That's what I was trying to
It's
figure out how to do.
missing from your header.
Yeah.
So it's trying to pull that stuff out of the header. And like if you click on show raw header, I bet you have a lot of empty. You have some stuff, but most headers are way longer than that.
Okay.
You could run it through astrometry.net before you import it.
It is also, you know what though? I'll say this, my students did this, and they were supposed to save the FIT file, but instead they saved a JPEG, and then I turned it into a FIT file.
Yep.
And so I bet that it lost a bunch of information.
Yep.
So if I go back to the computer and I download the fit file, that probably will have.
It probably will. But that said, we might still be able to get it to work. Go to
Okay.
WCS,
Okay.
and if we put in reasonable values, so no, but it's not letting you edit.
Yeah, but this was what I tried to then just like look up what the values were for
Yeah.
M13, et cetera. And when yeah, so you can see I can type something, but then it goes away. So I think there's
Type something in the appropriate range. Like I think you put like do like 12. Yeah, it goes away.
yeah. So and yeah, I couldn't put anything in here.
See, I've been able to edit plate solve.
And so I didn't know. I looked at these settings. I didn't know if there was something here that I had messed up. But these are all defaults.
Here, let me try on mine.
Okay.
Sorry, gotta load back in again.
Oh, here I can stop sharing.
Oh, and am I sharing? Yeah, I'm sharing. Okay. Let's see. I was looking at the R-band image. And let's see. I turned on source extraction just to see what. Let's see source. Oh, there they are. Okay, those are the sources it extracted that it's going to try to use. Now, if I click on this, it will load things in, but let me just try. Let's see. This is around. Zoom into that central pixel. 1848. Ah, took it on mine.
Okay.
But Seth, did you have your extract? Did you have your sources?
Let me see. Let me try that.
Yeah, I doubt that would. Let me find another one here where I haven't messed it up yet. It seems to be remembering.
Yeah, no, that still goes away.
So that's strange. Why would it do that for you?
Hey, Seth, what web browser are you in?
I mean, Chrome.
And Dan, are you also Chrome?
Yeah,
Okay, not that. Never mind.
that was gonna be my next question.
Yeah.
Let's see. Source extraction settings. Restore default. I don't think that matters. The
Well,
best.
I mean, I'll be satisfied if the answer is that my fit file is able to
Yeah,
view.
yeah. Try that. It could be that it's doing some check against the fits header
Yeah.
and seeing nothing there. It's blocking it out, not even giving you the chance to edit. But if that doesn't work, put it in an email and I'll make sure Vladimir takes a look at it.
Okay. Yeah. I am hesitant about sending you too many emails. I don't want to overwhelm you with all of my Afterglow issues.
It's okay. After I
Okay.
get through another week,
Yeah.
be far less busy,
Yeah.
as all of us will be, and I'll be catching up on backloads of emails. So
Okay. Yeah. Well, thank you very much. This is really helpful, as always.
my pleasure.
All right. Bye, everybody.
See ya.
Yeah, I had a quick question for you.
Yeah, go ahead.
I know we covered this a few weeks ago, but you were saying if we wanted to add or get additional hours on Skynet.
Yeah. So if you only need like a couple hours, I'll just give it to you. But if like you need a bunch of hours for student use, then it's a simple contract. Yeah, assuming your institution is willing to purchase the time, Skynet or UNC sells Skynet time for $75 an hour. And you know, the Opus labs are all done in half an hour of time. So
Right.
an hour last year well, but it's a minimum contract of 10 hours.
Okay.
So 750 and buys you 36,000 credits and we set up a group and make you the admin, and you can create accounts and distribute credits and pull credits back, and they're there essentially forever. The contract says they'll expire after 2 years, but that's just in case I ever have to shut Skynet down, and so I can legally get out of things. But otherwise, I don't take them back.
Okay, cool. Thank you, sir.
Sure. All right. See y'all.
Thank you.